Hi, I'm Chip. Thank you so much for having me and giving me a chance to talk about topics that I'm really excited about, which is automated model update and evaluation for machine learning. In the last few years, I have noticed that the industry is moving towards online predictions and continual learning. However, this shift doesn't happen in one go, but usually over multiple stages. For example, for predictions, usually people start out with batch predictions and then they move to online prediction with batch features such as embedding. And then they move toward online predictions with online features such as the number of views an item has had in the last 10 minutes. And similarly for training, it usually happens through like from manual ad hoc retraining to automated cadence-based retraining toward automated on-demand retraining, which we're gonna cover in this talk. There are two major enablers for online predictions and continual learning. So the first is fresh data access and computations, which usually refer to streaming technologies like Kafka, Kinesis, Flink. However, like streaming technology is incredibly exciting and complex, and it deserves like multiple talks. In this talk, we're gonna focus on the second enabler, which is infrastructure for CI/CD and monitoring. So to summarize, in this talk, we're gonna cover three topics. First, continual learning, like why continual learning and the challenges for continual learning. Then we're gonna talk about CI/CD for machine learning and how we can learn from CI/CD for traditional software. And the last is a topic that has gathered so much attention recently, which is monitoring. So first, continual learning. So in DevOps, companies have discovered that the faster you can deploy the model, the higher the return on investment. However, in machine learning, the speed of machine learning delivery is still painfully slow. So in this study, you will see that like 63% of companies still take at least a month to deploy a model. And you know that's like because of data distribution shift. After a month, the model performance has decayed probably quite a lot. So which means that by the time a model is deployed, it's probably no longer good, which means that it can cause lower business metrics and which leads to lower returns on investment. However, this is changing. A small handful of companies are able to deploy models really fast, like in out of hours, even like minutes. So in this talk by Whipple, we can see their evolutions of their machine learning delivery. They were able to like go from monthly deployment to deployment every 10 minutes. This is like really, really fast. So you might wonder like why do we care about faster machine learning delivery? So first, faster machine learning delivery allows our models to adapt to changing data distributions and rare events. So consider the case of Black Friday. So Black Friday is a very big shopping holiday in the US. However, it happens only once a year, which means that you can't really get enough historical data to train the model to predict accurately what users are going to do on that day. So to adapt to the user behaviors on Black Friday, you probably want to continually update the model based on data from the same day. And also because you can deliver model faster, the model performance will decay less, which can increase model performance and business metrics. And of course, faster delivery usually require automation of a lot of stuff, which can lead to like safe data engineering, data scientists and engineer time, which can be very valuable. And the last point that I'm like things like really interesting is the combinations of continual learning and edge deployment. So imagine that you can have any edge device like a phone or a smartwatch, and you can deploy a model to that edge device. And that model on the edge device can continually update itself to adapt to the user's behaviors without having to any centralized models training. So when they talk about continual learning, a lot of people think about updating models with every incoming samples, which is usually not the case. So the main point of continual learning is a manner in which the model is updated, which is stateful and on demand. So you're going to like stateful training as opposed to stateless training. So with stateless training, we train model from scratch each time. And with stateful training, we only update the model on new data. So you can see the difference between stateless training and stateful training here. And stateful training is also known as incremental learning. So you can see that easily training from scratch requires a lot more data, which usually means higher cost for compute power for training. And empirically, people have also found that when you refresh model with new data, the model can actually get higher performance. So in the case of Grubhub, when they switch from stateless retraining to stateful training, they were able to like reduce their training cost by 45 times while increasing their purchase through rate 20%. Okay, so you might think that okay, continual learning, like stateful training sounds really cool, but what if I have a new feature? When you still work, can I still refresh model with new feature or new data? So to answer the questions, we need to differentiate between two type of model update: data iterations and model iterations. Data iterations means that we have the same model, but we refresh it with new data. And model iterations that we means that you might have a new features or a new model architecture. So is there research like such as model surgery that can help you not have to train a model from scratch each time you have a new model feel like model architecture or a new feature. However, I haven't seen that a lot in production. So usually with model iteration, you still have to train model from scratch. So that means that stateful training usually only applies to data iterations nowadays. I hope that will change soon. There are four stages of continual learning. So in the beginning, when companies are still unlocking new use cases for machine learning, data scientists usually focus on developing machine learning models, and model update take a backseat. So people are probably only update models when some models are doing more harm than good, or when data scientists have time, which is pretty never. However, like when a company reaches a certain maturity stage, like maybe they have like 20 models in productions and it becomes impossible to manually update every single one of them. So companies might want to switch to automated model retraining. So usually for this to happen, you would need, of course, a scheduler to have you schedule the training job. You also need to gather the data and automate the data, pulling data from multiple data sources, which in my experience can be quite painful if companies don't have a good data platform. So a lot of them might wonder like, so how often should I retrain my model? And in this state, companies are usually answer the questions based on a gut feeling, like once a week sounds about right, or I want to retrain my model every night when the traffic is low and have idle compute. And it's not really like the optimal, but it sounds about right. And for the and then in this stage, a lot of companies train model from scratch, and companies might realize that training from scratch take a lot of time and a lot of compute power. So they might want to like switch from training from scratch to stateful training, which go to the next stage. For this stage, you when you keep on refreshing models with new data, you might want to keep track of the model lineage, like which model is refreshed based on which model. So you might have like version V1 and V1.1 and then V1.2. And so at stage three, you still train model on a cadence base like daily or weekly. However, for many companies, especially in B2B setting, when they have like a lot of customer and they have separate models for different customers, they might realize that they don't want to train own models on a fixed on a gut feelings based cadence, and they want to retrain the model smarter, more intelligently. So you might want to move to on-demand retraining. So you only want to train the model, or you only want to update the model when you need to. And for that to happen, you will first need a trigger mechanisms, and then you also need a way to automatically evaluate the model. So there are three different types of triggers that I have seen. So the first is a volume based, which usually is the most simple. So companies might want to like update models that receive more traffic more frequently. So you might have a rule like update a model every time the training data increase by 5%. It can be like performance based. So it can might say something like every time accuracy reduced by 1%, retrain the model. It can be like drift based, like every time a distribution shift happened, retrain the model. So there are two bottlenecks for continual learning. So the first is the fresh data access bottleneck, and the second is evaluations. So to retrain a model or to update a model, we need labeled data. So which require first to have to pull fresh data from different sources. So many companies pull data from data warehouse, which means that they can only pull data after data has been deposited into data warehouse. And for many companies, that process can happen daily. So if they only deposit data to their warehouse daily, then you can't really train the model faster than that. For some companies, they might want to pull data directly from the real-time transport like Kafka or Kinesis, which can allow them to get data as fast as the data is generated. To update a model, you also need labeled data, like data labels. And it requires ingesting labels. So if you have natural labels like from clickstreams, you will need to find a way to like extract labels from the clickstream. And that process can happen in batch like once a day, but it can also happen using stream computations, which allow you to access labels and join labels with prediction requests faster to generate training data. The second bottleneck is evaluations. Updating a model is easy, but evaluating that model is very, very hard. So the first challenge is that there are usually insufficient offline tests. Many data scientists only test their models against some static golden test set. However, the goal of updating a model is to adapt it to new data distributions. So it doesn't make sense to just evaluate it against some static old distributions. Therefore, it is also very important to evaluate models against online data in production environment through experiments like shadow deployment or A/B testing. However, online experiments take time. So consider the case of fraud detections. Fraud detections is a problem with class imbalance problem. So a lot of transactions are not fraudulent. So for A/B testing to determine whether a model is better than the other or not, it will have to see sufficient amount of fraudulent transactions, which might take like a while. So if A/B testing takes like 2 weeks to determine which model is better, you can't really update the model faster than that. And another challenge is with compliance. So for many industry, especially fintech, every model update will need to be reviewed to make sure that it complies with regulations, and the process can also take a lot of time. Okay, so we talk about CI/CD for machine learning, which will hopefully help with overcoming the evaluation bottleneck. So this will take inspiration from CI/CD for traditional software. So in traditional software, developers make changes in their local branch. And when they make a pull request into the main branch, it will kick off the offline unit test. And the PR, the pull request will need to be reviewed before it can merge into the main branch. And once it's into the main branch, it can be packaged into like staging environment before it can be deployed into productions, and then kick off the monitoring alerts that to trigger all guys at development, and that process is a full cycle. And very similarly, we want to propose the CI/CD process for machine learning. So in the CI/CD process for machine learning, data scientists can make a model update. And the model update can be like data iterations or model iterations as in a model with new features or new model architecture. And the data scientists can register this model update with a model store. And this process will kick off on the offline tests, such as test split or backfill test or regression test. So backfill test is like when you want to test a model against the most recent data, like data from the last 15 minutes or data from the last day. And once a model, and once this test result can be reviewed and approved, and if approved, it can be merged into the model store. And the model store can package this new model and evaluate this new model against existing models in shadow or A/B testing experiments. And then, if passed and approved, this model can be fully deployed, which also and then the model will continually being monitored, will trigger alerts or model retraining, and then the updated model can also be registered to the model store and kick off the entire process again. So for this to happen, there will be two core ideas. The first is that evaluations and deployment strategies will be very tightly coupled because you can't deploy a model before it has been sufficiently evaluated. And once deployed, the model will need to be continually evaluated or monitored before it can be monitor for changes or decay so that they can trigger retuning process. And we also, when we can see that model store here is at the center of the evaluation and deployment strategy. So we will need a model store that is much more powerful. So normal model store, like current model store, usually is just track and store model. So in our new paradigm, the model store will need to do a lot more than that. So we will need to also package and deploy models. And as we say that deployments need to be go hand in hand with evaluations, the model store will also have to evaluate new models against according to given evaluation and deployment strategy. So for each task will have its own model store, and then different people can propose tests. And then we have a predefined test suite, like A/B test, offline test for each task, and every model in the model store will be tested against this test suite. So this might what a standardized evaluations and deployment strategy might look like for a specific task. So whenever someone upload a model, that model will be tested against, like say, golden test set from week 1 and week 2, and the results, if passed, the model will be evaluated against a backtest against data from the last 24 hours. And if passed, then it can be promoted a shadow deployment. And then if approved, then the model can be deployed, replacing existing model. And then the new deployed model will be continually monitored for using some trigger to refresh models with new data. And the refresh model will also go through the entire process again. Okay, so we talked about monitoring, so I'm going to go into the next topic of the talk, which is monitoring. A lot of people think of monitoring in terms of distribution shift detections. However, this is not really the goal of monitoring. Monitoring, according to Wikipedia, is continuous assessment that aims at providing early detailed information on ongoing assess activities. In this case, assess activities are the model qualities, model performance. So what we really care when we monitor models is we want to know about the model performance. However, this is bottlenecked by the availability of labels or feedback from users. So if you're lucky enough to work with a task that has natural label feedback like Rexis, where you can determine whether or assume or can presume whether a recommendation is good or not based on whether user click on it or not, you might want to click as much feedback as possible. So for an e-commerce site, you might want to collect different type of feedback, like whether user click on an item or whether they add it to cart or whether they purchase it or whether they return it. So different type of feedback has different properties. For example, like clicks, user might click on a lot of items, so you can have a lot more clicks. But however, the signal of a click is pretty low. Like someone clicks on an item doesn't mean they like it. Whereas for purchasing is a lot more sparse because users usually buys a lot less items than the items they click on. However, buying is a much stronger signal than clicking. And when you monitor model performance, you also do not just care about the overall model performance, but also care about the fine-grained slice-based model performance. So you might want to see how it is performing on for different class or different slices of data or different subgroup of users. So it first allows you to uncover biases. So for example, if the model is performing really well for a subgroup user but not another, then there might be biases. But also it also help you uncover opportunity for model improvement. So if you see that models is performing very poorly for own data where the value of a feature is 0, and you realize it's you don't have enough of data for the slice of data. So you might want to increase, find a way to label more data with that property, so which can lead to model performance improvement. And for the tasks that don't have natural labels or the labels are too delayed to be used for monitoring, we will have to monitor others like proxy stuff like predictions and features. So when we do this, we make the assumption that changes in predictions and feature distribution will lead to model performance decrease. So monitoring in this case become a distribution shift detection problem. And you might want to ask okay, so how do we detect the distribution shift? So you have two populations. One population is data from today and another population is data from yesterday. how can we determine that these two populations come from different distributions, which means that the distribution of the data has shifted? There are two general approaches. One is a simpler one, is to compare statistics like mean, variance, mean, max. So if statistics have changed from today compared to yesterday, then you can presume that the distribution has shifted. The other method is more complex, is when you use two sample hypothesis tests, such as KS test or MMD. And both of them have some certain drawbacks. So for statistic approach, statistics are very distribution dependent. So what statistics you should look into depends on what distribution of the data the future comes from. So like for example, mean is a pretty good metric for a normal distribution, but it's not going to be very useful for long tail distributions. And also like statistics are easily inconclusive. So if statistics have changed from yesterday to today, so you can say that the distribution has shifted. However, if the statistics are still the same, it's not enough information to determine that the distribution have not shifted. And for two sample hypothesis tests, they usually don't work very well for high dimensional data. So if you have features like embedding, hypothesis tests are not going to do very well generally. Talking about statistics, it's very important to differentiate between cumulative and sliding statistics. Sliding means that the statistics are reset at the beginning of each time window. Many people I know I have seen work only with cumulative statistics. However, cumulative statistics can hide the changes in data. So in this example, you can see that the orange line show sliding statistic, and you can see that with sliding statistic, it's pretty rocky as in there are a lot of changes. However, the cumulative line is pretty smooth. So if you just look at cumulative line, you won't see a lot of changes. And when talking about distribution shift, we also need to keep in mind that not all shifts are equal. So for one, sudden shifts are a lot easier to detect than gradual shift. So consider this a distribution that looks like that. If we just look at the distribution from a time window and compare that to the last time window, you might think that the changes are not very significant and you might be inclined to ignore it. But little you know, but like over time, the changes can be very significant and can cause a model to decay a lot. And there are also like spatial shift and temporal shift. Spatial shift is when you have a new access point. For example, like user may have new device, so user behavior on a phone might be very different from user behavior on the desktop. Or you might have new users, like user from new country with totally different behaviors. And temporal shift are shifts that happen over time. So you have new same users, same device, but their behaviors change over time. Temporal shifts are pretty hard to detect. First, time window scale matters a lot. So consider as an example. If we try to detect whether a shift has happened on day 15, and we choose data from day 9 to day 14 as a source distributions, then you say that, oh, the day 15 looks pretty different from day 9 to day 14. So it's a shift. However, if you use the data from day 1 to day 14 as a source distribution, then you might realize that the spike in day 15 is just expected. So it's not a shift. And this also make it this difficulty is compounded by seasonal variations like weekend versus weekday. So when we choosing a time window scale is not very easy. First, like if you choose a time window that is too short, like in this case, then you might have false alarm. So you might detect shift when it's actually not a shift. However, if you choose a time window that is too long, then it might take too long for you to detect shift. So by the time you detect a shift, the damage might have already been done. So you might want to look into like shift time window at different level. You might have like look into hourly window and daily window. Many time series data tools allow you to merge shorter time scale window into larger time scale window. So you might be able to merge 24 hours time windows to create a profile for daily window. There are tools, RCA like root cause analysis tools that can also automatically analyze various window size to help you pinpoint exactly the time window when the shift happened. But you can imagine that it can be pretty expensive. So we talk about like when we don't have labels or feedback, you might want to monitor predictions and features. So I'm a very big fan of monitoring predictions. The reason is that predictions are usually low dimensional, which makes it very easy to visualize, compute statistics, and also do two simple tests on. It also like pretty fast. Like you can monitor things like, oh, if the predictions in the last 10 minutes are all false, then there's something probably very wrong. And also like changing in predictions distribution generally mean changes in input data distributions. However, this is usually not perfect because like the changes in prediction distribution can also be caused by canary rollout. So in either case, when you want to roll out a new model like to 1% of the traffic and then 10%. But then if that happens, then maybe the new model predictions are very different from existing model predictions. And for a lot of companies, that's something that they need to investigate. Monitoring features is by far like the most popular industry and most this is what most monitoring solutions focus on. So monitoring features usually go happen in two steps. Like first, like you need to generate expectations or like features. We go to feature schema or features statistics from a source distribution. In this case, it can be like from the training data. And then we monitor the schema or statistic in productions, and we see that if this schema or expectations have changed, then something is wrong. So here's some example expectations like can be like the mean, max, or median values of features, and you want that to be within a certain range. It's very popular, however, like it has certain challenges. The first is that it can be like very expensive to compute. So companies that don't just have like one model with like 10 features, they can have like 100 models, and each model has like 1,000 features. So this means that you have like 100,000 features. And you can imagine just computing like statistic for 100,000 features can be very, very expensive. Another aspect is that when you have a lot of features, it's very likely that some of them are going to change very frequently. And a lot of the changes actually not dangerous, like they're very benign. So like you might get a lot of alerts about things are changing, but then those changes like don't really matter, which cause people to like alert fatigue and just like ignore alerts altogether. Another challenge is the schema management because like the data might change over time, so it might different schema. So maybe during development you update the features and now the mean of these features now is different, but the model in production still use like the old schema, so you still need to find a way to map the predictions the production features to the old schema, which can be very painful process to manage. So yeah, that's it. Thank you so much for having me. And please reach out anytime via Twitter or email to talk about infrastructure for real machine learning or the CI/CD process in general. I also have a book coming out, and my publisher asked me to just promote that and talk. So yeah, do check it out, and hope to hear from you soon.